In this video, we are going to do a little bit of review and a little bit of new. I'll warn you, I have a cold, and so I may periodically clear my throat. But we're going to talk about work, which is review, and then power, which is something new. Um, all of this information is found in Chapter 7 of your textbook, which you can access via the MyLab and Mastering link on Canvas. And our learning objectives is that we're going to use force and displacement to quantify work. We already know how to do that. We're going to identify and calculate energy as it's flowing into or out of a system. We already know how to do that. We're going to define power as the rate of energy change. This is something new. And then we're going to solve problems involving energy and time. So there are a couple of different ways to conceptualize the concept of work. So I've already given you a couple, and we're going to review them. The first way to think about work is that it is the change in mechanical energy of a system, or in other words, work is equal to the change in mechanical energy. And mechanical energy, we've looked at three types: elastic potential, gravitational potential, and then kinetic. So one version of the equation is W is just equal to the mechanical energy final minus the mechanical energy initial, and this is all of them. Or the equation that I've given you, this is usually how the work energy theorem is expressed, is that the initial mechanical energy plus or minus any work done by external forces is equal to the final mechanical energy. And if you'll recall, the way that we thought about the situation was with energy bar charts. So I'm going to give you an example. Again, this is something we already know, but I'll give you an example just to remind you of what we're doing. So here is the surface of Mars. And we have our lander. I'm just going to draw it as a box because that's an easy thing. And let's say that it's floating down with a parachute. And initially it was at height 1 and above the surface of Mars, and now it's at height 2 above the surface of Mars. So if we do an energy bar chart, we know that we have kinetic, gravitational potential, elastic are our types. We have the system, and then we have kinetic, final, UG, UEL, and then energy that's dissipated or thermal energy. So in our system, we're going to have the lander and Mars. And then outside of the system, I'm going to put the air or the atmosphere. So we're going to consider that outside of our system. So when we think about dropping the lander, at H, we know that initially it has a certain amount of, I'm putting this in the wrong place, sorry. Initially, it has a certain amount of gravitational potential because it is above the surface. So I'm going to say that it has, I'm just going to give it 1, 2, 3, 4, 5. And then at height 2, it has less. So I'm going to say that it has 3 bars. I think I usually have a straight line here, so I'm going to do that. And then we also know that the lander is moving really fast. And so initially we'll say that it has some kinetic energy because it's falling. But then when the parachute opens, it actually makes the lander slow down. I mean, that's why you have a parachute, so that the velocity decreases. And so we'll say that the kinetic energy goes to this at height 2. So over here, when we count up, we've got, looks like 8 bars. And over on this side, we have 4 bars. And the question is, where did all of that energy go? And we know that what happened was the parachute slowed down the lander. And so we're going to call that work. And we know that it was 4 bars of work. And so this is work done on the lander by air. So if we do our work energy theorem, we know that we've got the kinetic energy at H1 plus the gravitational potential at H1. And then we know that we lost some energy due to work. We'll just call it's the work of air resistance. And then that is equal to the kinetic energy at H2 plus the gravitational potential at H2. All right, we know a couple of things. We know the formulas for everything. So we're going to call this 1/2 mv squared at H1 plus mg, remember this is Mars, of H1. And then the work is force times displacement. So this is going to be the force of the air resistance. We don't know what that is, but it's the force of the air resistance. And then this is going to be H2 minus H1. Now, we've got an interesting thing happening. I've got a double negative. We know that the energy is being lost, so I'm just going to put absolute value bars on that because H2 is less than H1. Well, it'll be a double negative, but we know the energy is being lost, so it's going to be that. And then 1/2 times the velocity at H2 squared plus mg Mars H2. And so this is going to be our equation that we have, and that we could use this if we're giving values for the mass and so forth. We could use this to figure out unknowns. And so that's one way to conceptualize work, is thinking about it as whatever change in energy we have between our initial state and our final state is going to be work. Okay, so work is the change in mechanical energy. A second idea is that work is the area under the force versus displacement graph. So if we think about the equation, in order to look at area, we're going to have force times the displacement is going to be area. But we know that this is the formula for work. And so we're going to say that the area is the work. Okay. So an example of how to do that: during which 2-second interval does the force do the greatest amount of work? So we've already done calculated areas, but I'll show you again just in case you've forgotten. So 0 to 2 seconds is going to be this area. That's a triangle, and so it's going to be 1/2. My base is 2 meters. My height is 2 newtons. And so this is going to give me 2 joules. Joules is the unit of work, okay? And then next one is 2 to 4 seconds. So that's this right here. So that's a rectangle. It's just going to be base times height. So the base is 2 meters. The height is 2 newtons. And so this is going to give me 4 joules. I know you can look at these and just say which area is the smallest. 4 to 6 seconds, okay, that's a weird area because I don't know exactly where that is, but I can look at this and tell that the area is smaller than 2 to 4. And then same thing with 6 to 8, I can just look at the area and see that's smaller. And so the major thing I wanted to show you is how to calculate area. It's just base times height. If it's a triangle, then you do 1/2 base times height. So the answer is B, 2 to 4 seconds. It has the biggest area. Okay, a third way to conceptualize the idea of work is that work is equal to the force parallel times the displacement. And so what we mean by that is, suppose that I am dragging my lander along. It's not going to show up very well, so I'm going to change to yellow. Dragging my lander along, and I'm actually dragging it by a rope, okay? So this is going to be my F, but my delta X is going to be this way. And so in order to calculate the work, I have to look at the component of F in the X direction. And so when I look at trig, I know that work is going to be F times the cosine of theta times delta x. And the reason why it's cosine of theta is because this is the component of F in the x direction. Okay, remember SOHCAHTOA, A for adjacent, and that's what we've got here. This is the adjacent or attached side to the angle theta. Okay, so I've got a couple of scenarios where we can look at this third way. So assume that the round object can only move in a horizontal direction. Okay, so it can only move this way, right? Which diagram shows an object gaining kinetic energy? So which diagram shows an object gaining kinetic energy? All right, so gaining kinetic energy means that the velocity is increasing, and the only way I can increase the velocity is when A and V are in the same direction. And what that means is that because F is equal to M times A, that means that F and V are in the same direction. Okay, so when I look at these, which ones are F and V in the same direction? It looks like only C has a component of F in the direction of the velocity. Okay. So when I look at C, I know that it has, let's do it so we can see it. It has a component of F in the X direction. It also has a component of F in the Y direction, but it's only this component that is in the same direction of the velocity that is going to actually make the velocity increase and therefore make the kinetic energy increase. I'm going to erase all that. All right, which diagram shows an object losing kinetic energy? Okay, so losing kinetic energy means that force has to be in the opposite direction of the velocity, and that would be because that means acceleration is in the opposite direction of velocity, and so that would be B and D. So again, B is just totally opposite, and then when we look at D, I've got component in the X direction that's opposite this, and so it's going to make it slow down. Then which diagrams show no change in energy? So that's actually going to be A because the force is perpendicular, the acceleration is perpendicular. So the only thing that's going to happen is it will change the direction of the velocity, but it will not change the size of the velocity. Okay, so what type of work is this? We're actually going to address that in our next set of slides. So we're going to call these positive, negative, and zero work. So we can tell how total energy changes by examining the external force. Remember, work, you have to have an external force. So we have positive work, the total energy increases, and that's when we know that kind of the train of thought, the velocity, let's do a color we can see, the velocity increases because A and V are in the same direction. Remember that speed up, acceleration, and velocity are in the same direction. And therefore, we know that F and V are in the same direction. So we are going to call this positive work. We are increasing the energy of the system. And so we can see two examples. They both point right, they both point left, or they both point up, or they both point down. When they're in the same direction, force and displacement, or force and velocity are in the same direction. That means acceleration and velocity are in the same direction. So my object is speeding up. Speeding up means gaining kinetic energy. So therefore, doesn't take a rocket scientist, even though we are pretending to be rocket scientists, doesn't take a rocket scientist to figure out that negative work is when the total energy decreases. And this means we are slowing down. And to slow down, that means A and V in opposite directions. And therefore F and V are in opposite directions. And I just want to, again, remind you, I already did this. Because F equals ma, we know F and A are always in the same direction. Because the A comes from F. Okay. So the external force and displacement point in opposite directions. Okay, zero work. So the total energy does not change, which means my velocity is constant. Actually, we should say my speed is constant. A couple units will figure out why I'm saying speed. Speed is constant, which means K kinetic energy is constant. And all this external force does, it changes direction. So the F changes the direction of the motion. Okay, only, right? And so that's zero work. Then we already talked about this idea of non-parallel work. So we can have not all of the forces causing a displacement, and you need to find the component of the force using trig. Specifically, we will use the cosine of theta in order to find the component in the direction of work. So let's do a quick example. How far can a mother push a 20-kilogram baby carriage using a force of 62 newtons at an angle of 30 degrees to the horizontal if she can do 2920 joules of work? Okay, so we're going to start with our basic work is equal to F cosine of theta times the displacement. And let's just make sure that we kind of know what we're thinking about. I cannot draw a baby carriage. Okay, so our baby carriage. We're going to have mom walking this way. And here's my angle, 30 degrees. Okay. And we want to know, so how far can she walk? Okay. So we know, all right, so we've got 30 degrees. We know that her F is equal to 62 newtons, and that's this right here. Sorry, my diagram is so messy. So that's my force that she's pushing with is 62 newtons, and we know her total work can be 2920. So we're going to solve for delta x. So I know that work divided by F cos theta is equal to delta x. And then we're going to substitute in 2920 joules, 62 newtons. Okay, times cosine of 30 degrees. And I need to get my calculator. And so if I calculated, I only did it once, so sorry if I calculated this wrong. We've got 54 meters. It's my delta x. Okay. All right, not all forces do work. So any force that's perpendicular forces do not do work. And there's another one that does not do work. Suppose that I am holding up a box and I'm just holding it up. Even though my muscles are certainly expending energy. If delta x is equal to 0, so I'm not moving the box anywhere, I'm just holding it. If delta x is equal to 0, then by definition, my work is equal to 0. So if we think about it, I know that if I'm just holding it there, we know that there is no change in gravitational potential energy. And we also know there's no change in kinetic because it's not moving. So that's 0. And so if there's no change in mechanical energy, then there's no work. Okay, so I know that seems crazy that I'm sitting there holding a box up and it hurts, and I'm using chemical energy. By definition in physics, there's no work done if there's no displacement. All right, last topic. Power. Two people lift a box to the same height, but one does it faster. Which one did more work? Which one used more power? So we've got a box, and we're just going to say that our box is going from H1 up to H2. So that we know that for each box, our delta x is going to be H2 minus H1. It's the same box, so we've got F is the same. And so this is going to be the same. So we know that their work is equal to F dot delta x, so it's the same for both. But now we have this concept of power. And so power is the rate at which work is done. And so the one who does it faster actually exerts more power. So power equals the rate at which energy is transferred or the rate at which work is done. The symbol for it is a capital P. Here's where it gets ugly. This is like one of the few ugly things. So the equation is power is work over time, or it's the change in energy over time. Now here's where it gets bad. The units of power are watts. So this is the unit symbol for power, but that looks familiar, doesn't it? This is the variable symbol for work. So you have these two weird things. You've got a different color. You've got, this is variables, but when we look at units, a watt is equal to a joule per second. So these are the units. These are the variables. So this is one of those places where you have to know sometimes watts stands for power, and sometimes W stands for watts, sometimes W stands for work. So it's just ugly, and that's the way it is. So let's do a quick example. Two physics students, Will and Andible and Ben Pumpin Iron, I don't know, are in the weightlifting room. Will lifts the 100-pound or 450 Newton barbell over his head 10 times in 1 minute. Ben lifts the 100-pound or 450 Newton barbell over his head 10 times in 10 seconds. Which students does the most work? All right, so let's think about the work. So the work is going to be 10 times, I know my force I'm lifting against is 450 newtons times displacement overhead. And so this is the same for both. And let's just say that my delta x is, let's say that this is 0.5 meters. I don't know how long people's arms are. That's probably way too long. So we're going to have 10 times 450 times 0.5. So that's going to give me 2250 joules. So remember, this is the force, this is the displacement, and this is the number of lifts. So both of them are doing this. But now we look at power. We have Will does 2250 joules in 60 seconds. because that's 1 minute. And so that gives us 37.5 watts, whereas Ben is 250 joules in 10 seconds. And so that's 225 watts. So Ben clearly delivers the most power. All right, so thinking about the lander, what do we know about our energies at the top of the lander drop? So when it's way above the surface of Mars, and then how does the energy transform during the fall of the lander? And how can we use this information to demonstrate that the lander will not exceed the maximum kinetic energy for a safe landing when it hits the ground? So right now at this point, do you know how to transform your knowledge of energy bar charts into determining the kinetic energy with which the lander hits the ground, assuming you know like the gravitational field of Mars and the mass of the lander and how far it's dropping? Okay, so our learning objectives are to use force and displacement to quantify work, calculate energy flowing in and out of an equation, define power as the rate of energy change, and to solve problems involving energy and time. I know you've only seen or done like a quick lecture, but how confident are you right now in terms of this material? Okay, so we're going to have a thinking sheet where you have the opportunity to practice these concepts, and hopefully it goes well. If not, ask me questions.